We face an unprecedented period of time when collective human activity is capable of altering the once stable state of Earth's environment. We are at a crossroads of political, industrial, and personal choice. If the right plan of action is set into motion and implemented in its entirety, there may be a planet worth living on for the generations of living species to come. Only one plan can achieve this. Part of this plan came into effect back in 1978 when the National Research Energy Laboratory conducted an 18-year study on the potential use of aquatic plant species as an energy source. This began a global movement of social and industrial entrepreneurs acting on behalf of the planet's well-being to place a new and exciting term into our vocabulary, the algae biofuels industry. Many believe it is the most effective response to climate change, peak oil, destruction of habitat, and a failing global economy. Since 1978, worldwide participation in the algae biofuels industry grows steadily with each passing year. As technologies and methodologies for production improve, so do the chances for our plan of global sustainability to succeed.
Hello, I'm Dr. Wan K1, the primary investigator of this microalgae project. As some of the fastest growing photosynthetic organisms on the planet, microalgae can solve many contemporary problems. Microalgae grow by capturing carbon dioxide, a greenhouse gas. They produce large amounts of lipids, which can be converted to fuels. They also produce valuable health products such as beta-carotene, astaxanthin, and vitamin E.
Norm Huner is the secondary investigator for the project. He has been studying photosynthesis for over 20 years and has more than 100 publications about microalgae in top biology journals. His advice on the biology of microalgae will be indispensable for the project.
Hi, my name is Darcy Small, and I'm a master's student working on this project. We started out growing microalgae in small windowsill cultures. The microalgae assimilate carbon dioxide from the air and convert it into biomass.
We are experimenting with different strains that yield large amounts of lipids to convert to biodiesel or sugars to convert to ethanol. This strain was isolated by our collaborators Ian Power and Gordon Southam. It grows rapidly in wastes from mines called tailings. It converts carbon dioxide into a mineral form that can be stored while also producing biomass that can be used for fuels. Commercially, most microalgae is produced in open ponds. It is the least expensive method. Therefore, we have built a small open pond which can easily be scaled up to study the growth of algae. A paddle wheel provides mixing, keeping the algae in suspension. We are bubbling air through the culture now. We will bubble high concentrations of carbon dioxide as found in gases emitted from smokestacks. We expect this to increase the growth of the algae. We are also testing the effect of magnetic fields on microalgae, which may improve their growth rate.
Once the microalgae are grown, they can easily be harvested by settling. The settled microalgae form a dense sludge which can be dried using the power of the sun. Once the microalgae are dried, standard oil extraction techniques can be applied to extract an oil similar to vegetable oil. Then, this oil can be subjected to a standard chemical reaction to produce biodiesel fuel. We've already produced biodiesel fuel from microalgal oil and characterized it using FTIR. Each year, Sarnia Lambton alone emits 16 million tons of carbon dioxide. Our goal is simple. Through lab-scale studies, we'll figure out a way to increase the growth rate of microalgae to make carbon capture and biofuel production using microalgae economical. Then we'll scale up our process until we're able to capture all of this carbon dioxide and convert it into useful products.